And welcome to the second part of this stream/video series. Yeah, we will do more work on our platform here. At least maybe a couple of hours. Let's see, I'm starting to feel a bit unwell, so I might end things early, but we will see how far we can get. Let's see. I just need to make sure that the setup is the stream is correctly set up. It seems like it. This is primarily a YouTube stream. I will answer chat from the YouTube side of things, and you need to be subscribed to be able to ask questions and interact. You need to be subbed for at least 3 minutes. Yeah, I'll do a generalized introduction before we start the recording of the next video. So last time we left off with a discussion of feature levels. And we actually had our API create a device. And we also set a name for it, even though we don't need to. I think what we need to do next is to set up some debug information, set up our debug layers so that we can get some debug information, and then we will move on towards doing more render-like stuff eventually. Yeah, but maybe we should just get into it. I've added a GitHub repo to the description where the code is available. Let me just show you GitHub. Just a bad programming guide / DirectX tutorial, which is updated since the last stream ended. So if you need to catch up, you can always download the GitHub project. I think it should be possible to build it on a Windows platform. No matter what. Using Visual Studio, of course. Right now I don't support any other build systems, but You'll have to live with that. Let's see. Does everything actually get put in the same directory? Yeah, it seems so. Okay. Well, we might as well get going. Let me see. Okay. As per always, I will answer questions in the end of what I expect to be cutouts of the individual videos in the actual video series on YouTube. Let me see. I just need to open some interface here. There we go. Also, like, no, maybe we don't need this. Well, let's change that setting. And we're public. Okay. Okay. I think we are set up. All right, here goes. We will start the video recording now. Hello and welcome to the next part of this tutorial series on how to create an application that runs on DirectX 12. Since the last video, I've created a GitHub repo. This includes currently every change made to the application up and including the fourth episode. So yeah, if you need to follow along or don't want to code yourself, feel free to pull the code. I'll try to commit in between episodes as well, so that whenever you start an episode, you should be able to pull the appropriate commit. Yeah. So that's the general plan. In terms of how to keep up to speed. In the end, this will contain the full application, which you can use for whatever you want. Feel free to comment, like, or subscribe, or even support the channel. Link is in the description and available on the channel itself. Okay, so last episode, especially the fourth episode, we got set up in terms of the DXGI factory, the DXGI adapter, and we also created an actual virtual device in DirectX 11 terms. We created this structure here, which is basically just a wrapper that on init creates a appropriate device. So next step will be to do further initialization, but before we do that, we would like to enable some DirectX debugging. We will create a debugging folder here where we will create a DirectX 11 debugger. We will also create a DXGI debugger, but we will start with the DirectX D12 debug. And we will create a wrapper for that, as well as all of the other API related elements. And let's do the engine here. Whoops. Let me just check that I'm recording. Yeah, I am. Okay. And we will, of course, create the same namespace here. As per usual, we will include RWRL and create a COM pointer to the interface, the debugger interface. We would like a static debugger. We only need one. And that means that we will have a default constructor. And we will also have a way of getting a reference to the debugger, which will be static debug, and will get us a reference. Let's see. We could probably do it inline, since it's going to return a static instance of this. There we go. Since we create a static variable, we need to instantiate it during I think it's instantiation time it's called. And that will be a memory allocation of this static interface. Let's see, D12 debug. There we go. We instantiate that, or rather allocate memory for it. Enable to in order to enable the debug layer, DirectX 12. We need to call this function on the D12 debug interface. Which is given by the example here. Let's see. We would like to be able to actually enable our what do you call it, debug interface. Which we will do. We will create a public method for that, where we simply will, as you can see here, we need to store a debug interface inside our debug controller, which is our debug singleton so basically this wrapper here can store our what do you call it, our interface itself. So we will make sure that we actually do not have a pointer already, meaning that if we already did this, this function shouldn't do anything. We created our evaluation macro earlier. Where we evaluate an edge result, and that is because this returns nothing, but this seems to be returning an edge result. Okay, let's d3d get debug interface, and we will do our macro here, and we will get the address of our thing here, and we will print out an error in case this doesn't work. We will of course call the get interface whenever we call enable, and then we would know that the pointer is set, and then we can enable the debug layer on this, and we can also, yeah, we could do an enabled function, but I don't think that we will do that. So this is basically the DirectX debug layer. And let's do enable that. Let's see. The debug layer here. Let's do that. Get did we do no enable, and that should enable our debug layer. Right now nothing is problematic, so therefore we won't get any messages. This could be disabled. Okay. This could be disabled during non-debug builds. You could also say that, let's see the factory here. Hello, welcome. The factory here itself, you could do separate versions for different builds. Should be coupled with the use of the should be coupled with the use of the debug layer. I can't move the live streams to the videos, so they will be in the live stream archive. But they will be there automatically. And so far we have built a debug interface like this, and I've also advertised the GitHub repo where you can download the code. Well, I can't do that in terms of backwards compatibility, but you can sift through different commits. I think so. Yeah, up until episode 4, everything will be the same commit. I think if you set it back to the old commits here, yeah, you can browse the repository before the commits, so you can actually look up the code. Yeah. I both linked the repo in the YouTube description, and also I linked the uh, YouTube on the repo, so everything is coupled. Yeah, but so far we've done the debug layer. It's basically a wrapper around the ID 3D ID D3D12 debug interface. As with all of the other components, I've done a static, or rather a singleton pattern where we only make one debug layer, which also means that nothing beside the runtime allocation controls the allocation of this class, and it's globally available since it's getting pre-allocated at runtime start boot time, or what do you call it, when the runtime starts the application. So, and we've basically set it to enable this debug layer no matter what happens. Next, we will create a likewise debug layer for our DXGI components. The nice thing about these different debug components is that the D12 debug component will give you runtime errors and error warnings and so forth in this actual console here. Let me see, can I increase the size of the output so that you might end up seeing it better? Can I do that? View, maybe. Increase text size for the output Visual Studio. Okay, tools, options, fonts and colors. Let's try increasing that a bit. Oh, whoops. That's not what we wanted. Oh, the text editor. Whoops. It was size 10. Well, we select the output window and we increase this to 14. This should be more readable. No, it didn't work on the debug window. I tried that, so thanks, but I needed to do something else. It works during the text thing here, but not down here. This should be more readable if you have problems reading the output of this part. Maybe I should just increase the size even more, since it doesn't bother me. No, it works fine this way. And let's see. Okay, it would like for this to be exported. We can of course do that. We will do the DXGI debug component as well, because as I've started to ramble on about, the D12 debug layer will give live information during the application. It will, for instance, tell you when your buffers aren't the right size and when you're trying to do something that you can't using the DirectX 12 API. The DXGI layer allows you to debug whether you have handled your resources in the API correctly. You can do a pretty nice function call with this debug layer that really makes you certain that you handle your well, I disagree. I'm gonna do the debugging because that's a part of actually learning how to use DirectX 12 and any other advanced um, um, graphics programming API. So yeah, we need to do that because otherwise we can't figure out what's going on in our application and where we might be going wrong. So we will implement uh, let's see, um, a COM pointer as well to hold this interface, debug, and as far as I remember, we can use the base one. We will do this static singleton stuff again for this class here. And we will, of course, create a static instance of this. We will also create a default constructor. And we will do this inline since it's not doing anything in particular anyway. All right. And we will, of course, instantiate that. Instance here. And we will implement the, oh, we already did that. We would also like an enable function here for this. And let's look up how we will use this enable it. Let's see, methods, report live objects is the method that I was talking about earlier. The interface is obtained by calling this. So let's do the exact same thing as we did for our other wrapper here. We will do a private function where we will get interface, and this will be exactly the same. If the current COM pointer doesn't reference anything, we can simply create or get the debug interface here. The first one, let's see, what do we have of different possibilities? We have the, what's the difference? Okay, we can do some thread tracking. Well, we're not going to use that. And we will get the address of our com pointer here, and error creating the DXGI debug interface. And get interface will be our method. And we would also like to be able to not only enable this, but we would also like to be able to get our live objects, which means that we can debug whether we have our object lifetimes correctly handled. If we released our resources, we simply call report live objects, and we need to look up this method. So we can look for specific objects. We would like to get information about all objects. We can also specify some flags. We would like details about the object lifetime. And we would also like to ignore anything that's not referenced. Because if objects reference each other but not by but doesn't get referenced by the application, we don't want that. Why does it bug? Okay, maybe I need to cast this as that. Let's see. Well, that was it. The combination of the flags. Because as I've mentioned, the DXGI debug layer pertains to different objects and their lifetimes, meaning that are there different resources that have not been deallocated or dereferenced in the internal API reference system. And the DirectX 12 debug layer allows you to see different DirectX 12 specific information during runtime. So yeah, the DXGI is more something that you use for checking whenever an application closes, for instance. Let me show you if I can show you an example. So now our application here would actually have the opportunity to do some object reporting. We can do some debugging here by maybe we want our application here to do an on destroy method, which will be called, oh, we already did that. Okay, on destroy, we would like the DirectX, maybe a DXGI debugger here. Did we specify that it's supposed to? Yeah, it's supposed to get the interface whenever we call this. Wait a minute, like this get, and we would like to report our live objects here. No, not that one. We want the one on the actual object. Did we get live objects? It's called instead. There we go. So whenever we close our application, we get a report on. Let's see. Did I not include that? Oh, okay. I probably need to include the debug header here. D12b dxgi debug. Where is this declared? Debug dxgi debug.header. And oh, maybe I don't. Did I? Let me see. Let's see. Do we need to dxgi debug.dll? All right, but thanks for dropping by anyway. Sure thing, man. Let's see. So we need to reference the DLL. Let me see, it can't find the method, so let's see which static libraries do we need to. Maybe it's the older version. Maybe it's the older version that we're actually referencing. Let's try swapping this. This needs a flex because this might be too old. Yeah. The problem was that this one is probably defined somewhere else, and right now we what do you call it? We use a newer method, and we have included our interface there. Let's see. Does it? Okay, this is dependent on the Windows platform. and it wants the DXGI lib, which we already have. So yeah, okay. We simply use this method instead to get our debug interface. Yeah, I would have to find the correct lib file to include it. Yeah, you can try asking in the comments. Otherwise, just tune in during the live stream, and we can do it during Q&As. All right. So let's see. Did we get done during doing our application stuff? Yeah, we do. Thank you. There we go. You may be able to see that our DXGI layer now finds a object that is live whenever this part of the application gets called. This means that there's something that we haven't released. Imagine that you wanted to do several windows or several um, different pipelines or view planes or whatever of DirectX 12 work. Maybe you wanted something to render only a 2D UI to one window, and maybe you wanted a 3D DirectX pipeline on something else. And you closed one of those windows, you would need to make sure that you handle resource what do you call it, resource dereferencing as intended. So this message here gets posted whenever we call get live objects. When we close the application, if we don't call that, nothing gets posted. Just a second. So yeah, our application here handles our live objects. We saw that we got a warning in regards to an object that is live when we close our application. We would want the renderer to, during our destructor here, check if the device that we store and that is supposed to go out of scope together with this API, if it's initialized and thereby have a valid pointer underneath it, we simply call the reset function of the com pointer. The com pointer reset function calls an internal release on the underlying pointer. So the DirectX API or the DXGI API for that matter would get a call to release the resource. These resources go out of scope whenever we're done initializing, so we actually don't need to release these components since it's done automatically for us. We reference the adapter in our device down here, which means that internally in the API, DirectX knows that a device points to a DXGI adapter. That was also the flag that we saw in the debug setup here. Let's see, can I find it? Here, we decided to ignore the internals, which means that we don't get internal reference counts posted because we don't care. We only want to be responsible for all the external reference counts because say we are the ones that manage that. Whatever the system needs to do in terms of cleaning up whenever there are only internal references is none of our concerns. Is not of our concern. Yeah, so this is basically a debug layer. In terms of the YouTube videos, I think I'll stop the recording and upload the video. The stream will, of course, continue. In the next episode here, we will start getting into the more DirectX related stuff in terms of getting up and running. Since we now have our helper systems, we have our device, we have a debugging layer, we can know a bit about what we're doing now. Now we can feel safe exploring how to set up the rest of the DirectX API here. All right, so I'll stop the recording but continue the stream. Feel free to comment, like, or subscribe, or ask questions. Yeah. Also, if you've been subbed for 3 minutes, you can do chat messages. I think I'll change that going on because that might be a long time if you're having the attention span of a modern day human. So let's do 1 minute instead. Yeah, I'll stop the recording and upload the next video. Also, we will do a GitHub push here. Let me see. Part 5 debugging. Okay. There we go. Let me just check the repo here. Let's check the commit. Let's see. Let's see, I pushed. Doesn't it update yet? I'm a GitHub idiot. Oh, wait a minute. Commit, of course. Okay. Did we commit that? Commit that and push that. Of course, yeah, I need to remember the order in which I need to do things. I'm so silly. Okay. So yeah, now you can swap back. in terms of the history. You can view the repository like that. You can, hi there. Well, I haven't done it so far, since I have some interest in um, in machine learning. I might do it in the future. All right, let me just upload this video here. I haven't done a build system yet. I I am not really um, really that great at Clang or CMake or whatever build system. Um, the repo supplies Visual Studio solutions and project files. So that's the unfortunate build system we have so far. But uh, I'll definitely bear that in mind in terms of future requests. Maybe it's something I should learn uh, more about. All right, let's continue this series here. I'll start the recording since I uploaded the next video. Hello and welcome to this episode. I've updated the repo. Uh, this one doesn't show. And you can look back at old versions. I made a commit that is called part 5 debugging, which is an update to the repo. As far as I know, you can download old repos, right? Let me see. Let me just check this out. If this doesn't contain our debugging, yeah, you can use the GitHub system to access old versions of the code in between episodes. The latest repo is commit is up to date. Yeah. Okay. In this episode here, we will start messing around with something called a command queue. And a command list, since we need at least a command queue to set up our so-called swap chain, which will handle when we want to render stuff to the actual screen. The way I have done it so far has been somewhat different every time. Since we are not creating a design here that is supposed to be easily multi-threaded or handle special case command queue stuff. As for now, I won't be doing anything too complicated. Yeah, so you can always develop more advanced components if you want that. We will do a wrapper for the command queue as well. We will only use one type of command queue, which is the, I think it's called the graphics command queue. Let me see. We have the compute command queue and we have the copy command queue, but no, it's called command queue direct, I think. Blah, blah, blah. Lots of examples here. Or rather, not lots, but some examples. Anyway, we will do commands as a subfolder here, and we will create a new wrapper class that will be our D12 command queue. And the command queue is, as you'd expect, something that simply queues up commands. If you're used to working in DirectX 11, even though I have no experience doing that, I suspect that that you don't know the command queue very well, since it's part of the API that got more explicit in DirectX 12. Excuse me. I just need to check some stuff here in terms of the stream setup. Yeah, okay, everything's fine. And we will, as per always, of course, include our com pointer here. Let me just swap this. And we will store an interface to the 3D12 command queue. Inside of this, we will allow our application to create an empty command queue by using the default constructor. This will be a direct type command queue wrapper. Yeah, the command queue itself will store a so-called fence, which is a synchronization object, probably, without me being certain, related to the synchronization component that you find in in Vulkan, which is called semaphores. Each command queue will have a fence value that is updated internally and stored on the command queue interface, or rather, by referencing a fence, the actual fence value gets updated internally in the API whenever the command queue has done something up to the point of a certain fence point. Let me show. I will show you that more in detail what that means, but it's basically a synchronization object here where you use that to, let's do this, and let's actually do it in 64 bits, where you kind of like, how should I phrase it? Now I lost my train of thought, but anyway, defense is something that handles synchronization points on the command queue. Whenever the command queue is done with a set of command list recordings, the command queue will signal the fence and set it to a certain value. You can always query the fence to get the latest completed value, which means that you can always ask the fence how far is the connected command queue to being done in terms of work submissions. But it will probably make more sense whenever we get an example up and running. So we would like some inline functions here where we return a uint 64 and we should be able to ask our command queue whether for a get current fence value. I would like to underscore it to make certain that we don't confuse this function with something that is on the actual command queue interface. You could maybe add a W here. Maybe you want to preface it with a W for the wrapper. Yeah, maybe that's more obvious. Or maybe an M for the member value. Usually I don't preface functions that clearly, but this might end up confusing ourselves down the line. We simply return the current fence value. We would also like to be able to get a fence pointer to our underlying underlying fence. In case we want to query the fence directly about something. All right, we will return to the command queue in a short while because we're not done with this command queue here. Let me see. Let me just close some of this stuff. We actually don't need the device. We could maybe use the helpers. We don't need the application for now. But we would like our renderer API to have a command queue allocated that it can use to record commands. So let's do a D12 command queue, which we will store on the renderer API. And we, of course, want a way to initialize our command queue here. And I know from previous experience that it will take a device here, since you will call the initialization of it on the actual device. The way that we will create or initialize our command queue is to create the resources needed, which means the queue itself and the fence. And if you're ever in doubt how to create anything in DirectX 12, simply just Google create whatever component and then DirectX 12. As you can see on the interface for the device in DirectX 12, there's a command called command queue. It would like our old IID PPV macro in terms of where should I store the pointer to the actual underlying interface, but it would also like a command queue description. And we will need to fill out that. So description. And we should always, if it allows us to, initialize it as 0. Some people might be asking, well, why aren't you using const and so forth in your method declarations? Well, sometimes the DirectX API prefers to be able to change different pointers. So that means that we can't simply pass in more pass in constant values. All right, but so we want to fill out the structure. The first one is the type. Let's see which kind of command queue will we use on this, or rather command list will we use on this command queue. As you can see, there are several types. The direct, a command buffer that the GPU can execute. It doesn't inherit any GPU state. The bundles inherit some GPU state. It's just a bundle of commands. I rarely use it, at least for now. And we can do the compute command lists. That is for asynchronous compute, or yeah, for instance, some machine learning algorithms where you don't need the graphics output. There's a copy command list where you can copy information over the PCI lane from the CPU to the GPU, or for that matter, the other way around. But yeah. And there are some video decoding and processing command list types. We will use the direct since it's pertaining to commands that the GPU can execute. Next, we will specify our priority. For this application here, we want the highest priority. Let's see. Global real time sounds great. Well, okay, maybe we just want high. I haven't tested the excuse me, I seem to be catching a cough, which has been building most of the day. Well, next we specify the flags. We don't want any flags. And lastly, we set a so-called node mask. This pertains to if we do SLI related to the dual GPUs setup. I won't support this, but know that if you want to support SLI, which is, as far as I know, not that common anymore, you would need to mess around with the node masks. I can't really help you in terms of that. I think that's a more advanced topic. All right, so now we have our description, and we can simply call our YouTube evaluate H result, and we can ask our device here to create a command queue for us. We will pass in our reference to our description here, and we will pass in our IID, PPV args here, and we will of course allow it to store it in our com pointer on this wrapper here. Error creating command queue. And next we want to create a fence. Well, create fence DirectX 12. Well, wouldn't you know, it's also on the device. We want to set an initial value and then some flags. You can do cross adapter sharing. Well, it's not shared, so we will set no flags. We will of course do the YouTube evaluate H result here on the call to create the fence. We will set it to 0, and we will set the flags to 0. None is 0. And then we will do IID PPV args and store our fence here on our fence address. And we want to pass out a error creating the fence if this doesn't succeed. Okay, what does it want? Fence flags, okay, it wants the actual flag here. It's an enum, okay. I'm sorry, I could of course cast it, but yeah, I've already done or started up doing the command queue wrapper here. So that follows I just talked a bit about that. But let me see, I can maybe do a quick summation on that. Let's see. So the type is pertaining to what kind of command list you expect to commit to this kind of queue here. You will use different queues for different types of command lists. You can do command lists that only handle copying of data from the CPU side to the GPU or the other way around. You could do command lists that only do so-called compute operations on the GPU. And there are limitations to what each command list can do. We might, when we do the command list, wrapper actually see a specification on the different types of command lists. But yeah, you can do asynchronous copy steps while working on, for instance, a direct type queue in meanwhile. So yeah, there are different ways of doing multiple things kinda at once, as long as you make sure that everything is synchronized. But for our use case, we will just use a single command queue that can do all our graphics calls. In my own project, I do two command queues right now, and I'll probably implement a third when we do more advanced shader stuff. You also get to set the individual command queue priority. For something like direct, you would prefer something that is high of priority, since it will be your main command queue that is supposed to handle most of the heavy lifting, since it can do a lot of different graphics calls through a direct command list. So yeah, you definitely would want a high priority on that. This is direct command queue. Yeah, you could do a copy command queue. It's only for the initialization, and it's just a wrapper. So a lot of the things that we do are kind of like overall wrappers that make our lives a bit easier. Okay, so for now we are done, excuse me, with this part of the command queue. Oh, wait a minute. No, we're not. Because this command queue here actually has allocated resources on itself, whenever we destroy it, we would have to make sure that the resource pointers are reset appropriately. So if we don't do that, we will get a warning from the DXGI debug layer. Let's do a internal function, or rather a public function here, that is called release, because we might want to reset the state of the command queue for some reason. Suppose you implemented that you can specify the actual type of the command queue when you initialize it. You might want to reset it and initialize it as something else. Either way, we need to check if our allocated fence, or rather stored fence, actually is allocated, and then we need to reset that pointer so that it decreases the reference count. Then when you destroy your command queue, you of course call release. Let's just initialize here the command queue. Command queue initialize, and we would like our device here. For instance, if I disable this, when we close our application, as you might see down here, let's see, we have several warnings. We have a problem that we can't dereference our device. That might be because we have both a command queue and a fence that actually references our device. So even though we might call the reset on the pointer itself, it's still referenced by our other objects. So this is the power of the DXGI debug layer. It tells us, hey, you forgot to release these things. And we will also, of course, check if this has a pointer set, and then we can call the reset here. Okay, so now we should have no problem when we close the application. Well, oh, wait a minute, this goes out of scope a bit too late. We want to manually actually call release here on our command queue. And we would probably like to do it in the reverse order in terms of initialization. Okay, there we go. Well, we still do end up in a situation where maybe we also need to be able to, maybe this doesn't go out of scope before our application. So maybe we want a release function here where we move this and call release here instead. And then inside our application, whoops, on destruction, we want to call renderer release. And then we want to, excuse me, post how many things we forgot to release. Okay, now we're good. Great stuff. Yeah. So this shows you how the life cycle of different objects / classes in C++ are handled in contrast to the manual handling of reference counting and object lifetimes in terms of the DirectX API. All right. So that is it for our command queue. Well, the destructor does execute, but since we are reporting the live objects when we try to, no, it's a matter of when things get called. So the destruction of, oh, maybe you're lagging or a bit behind me, but yeah. It's related to when the actual classes get deallocated and the destructor gets called in comparison to the scoped pointers. So whenever we call this debug layer here, we haven't destroyed our actual render API because this class hasn't been destroyed. No problem. Anyway, this now works. So we will, for every object that has a set of underlying com pointers, which will increase reference counts to different objects externally, we will make sure to implement a release function. No, I'm not done with the command queue, but I've initialized it and created it. So that's a step, but right now we can't do anything. We only have a command queue, and we would like a command list as well to couple with that command queue. And we will also create a wrapper for that. And we will also create methods that link these things together. So we will do a namespace here again. as per usual. Um, let's see. And a command list is, as you would expect from our experiences so far with something that something that is called a list. It is of course a list. What is it a list of? It's a list of commands. Wouldn't you know? That's awesome. Anyway, we will create a default constructor. We will create a initialize function. As we're trying to do good practice, we will create a release function. And we will of course make a destructor that will call the release function whenever we need to. And the thing about command lists is that they are kind of like an interface that needs some kind of buffer. So if we create a command list here, we have to specify the node mask that is for SLI, so it will be 0, and out of interest for us, we will create the type, which we saw during a bit about in our command queue wrapper. We will also need something called a command allocator. And this is actually just a buffer. As you can see, it represents the allocations of storage for graphics processing units and their commands. So imagine this being a vector of commands that the command list can use to store whatever information it would want. It can have several adapters, but it can only use one at a time. You can never deallocate a allocator before the command queue has executed every command on the command list and thereby in the actual command allocator. You can also set a default pipeline state. We won't be doing that. Right now. We will return to pipeline states and do them manually later on. So yeah, let's create a wrapper for this. We know that since we will be calling our device here to create our command list, we know that we would need a pointer to our device. Let's see, I missed a capital D here. We know that we also want a command list allocator or command allocator. So let's just store it in our wrapper because it will we will only do a single allocator per command list in this implementation. Excuse me. So we will store a command list allocator. We will create our initialize method here. Maybe we should just make Visual Studio declare some and define some function outline here. Yeah, a command list, command allocator is just a buffer. It's just internal storage. It also means that if you keep on recording commands, you might end up in a situation where you have a GPU/CPU related memory leak. Usually memory leaks are seldom in C++, but I've actually experienced a command allocator that had a memory leak. So Visual Studio will show you increasing memory usage in that use case, in that situation. So you can use your internal monitoring in terms of detecting that. But yeah, uh, it's basically a buffer. So of course it can increase in size and it needs to be managed. All right. Um, we promised ourselves that we would call release. And when we call release, if we have a valid pointer, we will call, let's see, reset. And since we also did an allocator here, if it has a valid pointer to an underlying interface, we would also like to reset that. Excuse me, can't really help it. Anyway, we promised our command queue here that we will only use direct command lists. It doesn't matter because we actually want to be able to use every graphics call. Yeah, exactly. It's just a self-increasing buffer that is used to store the commands assigned to the command list. And when you submit the command list, as we will see later, to the command queue, um, um, uh, uh, you would have to manage that buffer um, when you are done doing whatever commands you need to do on the command queue and the fence value reaches a certain point, you can reset the allocator and reopen the command list. But we will get into that later on. Right now we are only doing some wrappers and initializations. We're not doing actually any work yet. So let's do a YouTube thing here. Let's see. We saw that our create command list method would like a pointer to a command allocator. So that means that we need to create the command allocator first. And for that, we just need to specify the type of the command list, which is direct here. So we will do that. YouTube evaluate H result. And we will use our device here. If I can spell it correctly. Create command allocator, and we need a direct type, and then we will just store it in our COM pointer here on this wrapper. Allocator, let's see, get address off, and we want to error creating command allocator. And there's that, and we do another YouTube evaluate H result, and then we call our device create command list, and we don't use a node mask since that pertains to SLI, which we don't use, and we want a pointer to our allocator. Isn't it great that we actually decided to do that first? And then a null pointer because we don't have a specific pipeline state set at initialization time here. We might have, you might have in your application, but at least we do not have it in this application. All right, let's do that. Sorry, I missed the buttons here. So now we initialize our command list. And again, we're just doing wrappers that will make our life easier and this area a bit less cluttered. You could do everything more explicitly if you wanted to. You could do it all in the same function. Yeah, you could basically do whatever you want. I like to create wrappers. I know if we were doing it more C style, we wouldn't be able to do that. Maybe that would be a fun project to do everything in C instead of C++, but yeah, since it's what I'm most familiar with. We do it like this. Let's see. And we, of course, need to pass it our device here. And let's see, does everything compile? Everything compiles. Did we get any errors? We do not release our objects correctly. It complains that we didn't remember to call release on the render API, which is absolutely true. There's no way to hide from the DXGI debug layer. Is it satisfied now? It seems like it's satisfied. Great stuff. So this is our basic wrappers. We will return to these wrappers in the future, since we will be needing to couple them. Right now we haven't any work to do, so it wouldn't make sense to give an example right now. DirectX 12 requires some setup in terms of wrappers and different methodology to be in place to be able to do anything. This means that I will be ending this video here. The stream will continue and I'll do the next step in the next part of the stream and the video series. We have a question here in terms of what I've done. It's basically explained here during our initialization step. We enable the debug layer. We create a factory. We use that factory to get an adapter. We just output some stuff here. Let's see, we could scope this so that it's obvious that this is not related to the actual initialization. Debugging console output for debugging. Then we end debugging output. Then we initialize our device using our adapter that we fetched. We set a name for our device. As you saw during the DXGI stuff, we use the name main virtual device for our current device, and we initialize a command queue with its fence, and we initialize a command list with its command allocator. So this is more initialization. We're not done, and we will probably spend several videos getting done. Next, we will do the swap chain setup, which means that we will actually have some sort of output to our screen within the next video. But in order to set up our swap chain, we needed a command queue, and we will explain more why in the next video. But I'll end the recording here and continue on in the next video segment. All right. If you find anything helpful, inspirational, entertaining, feel free to comment, like, or subscribe, or even support the channel. If you got interested in game development, feel free to tune in during my other live stream here on the channel. All right. See you in the next one. And here on the live stream, I'll just upload the video. Let's see. I just need some stuff here. Some boilerplate text. Let's upload the video here. Let's set it to publish immediately. And we also need to do the commit. Bup. There we go. And let's do the synchronize. Part 6, command lists and command queues. There we go. All right, let me see. The unnecessary parts. I'm unsure what you mean. Let's see. This is part 6. Oh, well, wait a minute. Because I start the recording and end the recording. That means that I would have to edit the video, so yeah, I'm not gonna do that. I think well, yeah, I'm not gonna bother. Let's see. Didn't we get the commit at probably? Maybe I didn't. Maybe. Oh, we need to do the push, of course. Okay. And GitHub should be updated. There we go. Yeah, I'll do the swap chain now, I think. uh, let's see. So we're done with that. Okay, let's continue. I'll start the recording in a sec. Okay, I'll start the video now. All right. Hello, everyone. During our last episode, we created some wrappers for our command queue and command lists, and we got to initialize them. The GitHub repo is updated with the episode source code. You can always use older commits to go back to older episodes and follow along if you want to. As you can see here, we have everything back to episode 4. And yeah, during this episode, we will prioritize doing something to our output here. Right now, we have this window. It's just a basic window, and nothing actually happens to that window. We have some tools at our disposal in terms of doing something at least on the GPU. We can do command lists now, and in the future we will be able to submit those command lists to our command queue. But right now we don't have anything to use in terms of getting output to the screen. That is what a swap chain does. The swap chain is actually related to the actual hardware itself, so it's part of the DXGI interface layer. So we will create a DXGI swap chain wrapper to help us create our different functionality on the swap chain itself. We will, as per always, do the engine namespace, otherwise we go insane. This will also contain a COM pointer wrapper. As per usual, you kind of know the drill on how we do the wrappers here on the channel. And I do not mean the musicians, but the software encapsulation of different items. And that was me trying to be a bit funny, even though I'm not sure I even found that funny myself. We will do the swap chain here. And we will, of course, allow our system to create a empty swap chain for later initialization. We will also like to create a destructor. And of course, we do great DirectX practice. So we will also provide a release function where we will check if the pointer here is set. If so, we will release the pointer. We will also call release on destruction here. So a swap chain. What is a swap chain? What is a swap chain? A swap chain is basically this. Wikipedia. We have a screen buffer. We have one or two back buffers, and we have what we show on the screen. The screen buffer is always shown on the screen. So the swap chain makes sure that we kind of like have something to render to while we are showing the last frame. This means that it has several buffers, 2 to 3 usually, we will do 2, which it kind of like swaps between so that you get output to your screen. The buffers here are called render targets during several parts of our pipeline. Because they are targets to render to. This means that when we create a swap chain, which is a bit more complicated of a wrapper, we would like some global variables to let us know how many render targets, i.e. how many buffers we have available. We will create a global variable here that is called max swap chain buffers, and we will do 2 of those. We will make sure that we include them in our PCH file. And we shouldn't be bothered anymore with that. The way that we store buffers, let's see, you can see here, DirectX 12 swap chain. We have to do it on the factory. They recommend that we don't use this one since DirectX 11.1. We want to create it for our handle to our window instead. Anyway, we need to use our device to create it. We need our handle to our window. We need a swap chain description. I'll open that in a new tab. And we will need to do a full screen description. We can set it to null. We will use windowed mode. We have some optional outputs. And we, of course, need to store it somewhere. So let's look into the swap chain description. It describes how big it is, the format of the render targets, some stereo mode, I can't actually remember what these parameters do in detail. Let's see. We also need a swap effect. Flip is preferred in DirectX 12 as far as I remember. Yeah, we need a buffer count, of course, which is what we just set as a global variable. We need to set a usage, meaning that this will be a render target output, since we will use our buffers for render target outputs. Let's see, we could maybe do other kinds of for the buffers. Yeah, maybe you wanted to maybe render it to the CPU or something. I probably think that this is done during the compute shader stuff. Anyway, the swap effect we already discussed. Flip sequential. Let's see, swap effect, flip sequential. It will persist the contents of the back buffer after you call that flip mode. We can also do flip discard. This cannot be used with multi-sampling. Yeah, there are different considerations in terms of doing that. Anyway, the complicated thing about the swap chain is that it will also need to provide its own buffers, and it's generally a more tricky component to create a wrapper for. Therefore, this will be probably a bit more slow video. But yeah, we will have to create some internal buffers. Buffers in DirectX 12 are resources. Resources in DirectX 12 are just resources. They don't have any type. You are also, excuse me, you're also allowed to map the same resource to different types of resource. The system doesn't care. Therefore, we use the resource type here for every kind of resource. Since we will be flipping over our buffers, we want to set a total buffer count when we initialize the swap chain. We also want to set a current buffer index, and we want to probably store the width and height of the buffers in terms of if we ever end up resizing the swap chain, we would also have to recreate the resources. Other than that, we also need something else. Since the GPU might want to access the render targets during the application runtime, you would have to declare not only the resources themselves, but also a so-called descriptor slash called a view. It's basically the same thing. A view is the same as a descriptor. That tells the graphics pipeline that this resource that is allocated somewhere in memory is actually able to be used as a render target. And if you ever need a render target, you can find this so-called pointer in a special place that I'll mention afterwards. Yeah, so it can do lookups in terms of these resources. So not only do we need to create the resources for the swap chain for it to render something, we also want to be able to store references to these objects with information about their kind of like buffer dimensions. What is a slice? What is the size? Stuff like that, which is useful to know when we try to access a buffer with only a pointer. So we will be creating something called a descriptor heap. 12 descriptor heap, which will hold our render target views in a heap. So the description of each resource will be, of course, a render target description, and it will be stored in a heap that holds all our render target views slash descriptions. All right. The thing is that the way that these things are stored differ from GPU vendor to GPU vendor. So we're not done pre-declaring values here. We also need to store Sure thing. Thanks for dropping by, and good luck. Have fun. We also need to store some information in case we need to redo the resources about how large allocations our current hardware does. Well, this is actually relating to the allocation of the buffer itself, or rather the descriptor itself. So the amount the pointer has to be increased to find the next render target. Okay. We saw that our swap chain here needs to take at least a IDX VI factory. Since we have a factory version number 2, we will take that factory and a handle to our window, and excuse me. We will need that at least to be able to call our method of creating the swap chain. As we saw here, we will use that. It's also a factory too, so that's great. Okay. We will look up this function again. We also need actually the device. Wait a minute. This is a pointer. Oh, it's for the direct command queue. So we actually also need a command queue. Let's do it here. And a handle. Let's say, do we need anything else outside of this? No. Uh, we will expand upon this method later on. We need to, let's see, does this return? Yeah, it returns an edge result. And we call our factory here to create a swap chain for a handle to a window. We will know that this needs a command queue pointer, not a device. We will also need our handle, and we will need a swap chain description. We will give it one in just a sec. And then we will get our address here. Our current com pointer. And we will, of course, call error creating swap chain. Let's see. Let's see if we do ddppv args instead. Will it stop complaining? Well, let's see. Okay, let's update our swap chain here to 1. And then we can do get address off again. Yeah. Okay. The thing is, though, that we need a swap chain description. Also, not full screen. And we will, of course, initialize that as 0. Did we did we do that? In our command queue? Yeah, we did. Okay. The structure here holds a width and height information. So wouldn't it be nice if we had some kind of information about exactly that? We even have created member variables to store them in. Let's do some const uints width, height, and copy that over to our method here. We will set our description here, width to our width, description here, height to our height. What else do we need? We need the format. It's the buffer format here. Let's see. We will need a format to choose from, the DXGI format of floating point numbers, one for red, green, blue, and alpha, 16 bytes. That seems fine. Let's do the stereo bool. Let's do false for now. Then we need a sample description. This is related to multi-sampling. We will set that as a count of 1 and a quality of 0. Then we will do our description buffer usage, which will be our DXGI usage render target output. Let's do look here, buffer count. We will use a global here. We will also store that global buffer count. I know this is kind of like redundant, but maybe we wanted to be able to change or reduce the amount of swap chain buffers. Next, we do some scaling. Stretch, none. No, we won't be doing any scaling. Next, we do our swap effect. DXG flip discard. Let's try that. It just swaps the pointers as far as I know, so it probably doesn't matter. Next, we do the alpha mode. Yeah, we will ignore the transparency behavior. And then we will do some flags here. Do we find anyone interesting? Any interesting? Allow tearing, variable refresh rates. We probably want to allow that. DXGI, swap chain, flag, allow tearing. And we also need to use a swap flip, but we're already doing that. Let's see. Yeah, we would like to allow switching. Did I DXGI swap chain flag allowed mode switch? Yeah, we will do that. All right, and let's pass in the description. Well, it was after the handle, we pass in our description here, and it's by reference. All right. So we actually created our swap chain here. Does our renderer store any information about our width and height? Maybe it doesn't need to do that. Yeah, it does. In the future, we will need to do that. So we will do a uint width and a uint height. And we will actually pass these values in to our uh, renderer API at initialization time. Let's see. We will do that, and then in our application where we actually, let's see, call this. We don't need these for now. Maybe we want some values here. I know we will store them different places, but we want to access these variables, and they are not that big to store. Let's do actually these m width and m height. And we pass along the width and height during our initialization step. We want our m width to be our width. We want our m height to be our height. And then when we want to create a swap chain here, since this is a DXGI thing, we will actually create that before the DXGI swap chain, and we will initialize that by getting our factory pointer, our command Q, Q pointer, our handle to our window, and our width and our height. Let's try doing that. Did we implement the release? Yeah, we did. And up here, when we call release, m swap chain, call release. All right. We have some errors here. Okay, We also have some stuff related to our stored member variables, YouTube API here. YouTube API here. Let's do a YouTube API here. Let's do I think we did. Oh well. It's the member variables of different stuff. Okay, undeclared identifier. Well, let's include this. The command queue. Okay. D312. Okay. Include the global settings as well. All right, great stuff. And do we have any live objects? Okay. Let's see. You can already see the effect of the D12 debug layer. We have a problem. Let's see. Didn't we specify the correct format? I think we did. Let's see. But it's only support this format. Is that different? No. Oh, flags. Whoops. There we go. And now we do not have any errors. Okay. So now we successfully created our swap chain. But we haven't really created anything that it can use. So we can't really use it yet. And I think a nice scope of this episode here will be to actually render something to the screen. And remember, I specified that we would need to initialize these resources to ever be able to create or rather use the swap chain. Let's see. Let's store the width and height for future use in case we want to flush the buffers. Okay, we will do the actual descriptor heap, which is the heap that stores our pointers to our render targets. This is called by using the device. So since we haven't supplied a pointer to our device, we also need to do that. Maybe we do it as, well, we don't really care. I do think it's always nice to include the device here. as one of the first parameters. In our renderer API, we also need to get the device pointer here. Then we will create our descriptor heap. We need a descriptor heap description for that. Let's do RTV heap description here and initialize that to 0. We will set a type. And as you can see, we can do render target views as our descriptors in this heap. We can do the number of descriptors according to our max swap chain buffers. Next, we can set our flags and our no mask. Let's see, do we have any flags? Shader visible, we definitely do not need this to be shader visible because oh, wait a minute, I spelled this wrong. RVT, RTV. RTV, descriptor heap, flags, none, RTV, descriptor heap, node mask, none, because we don't do multi-GPU. We can do a YouTube evaluated edge results where we ask our device to create a descriptor heap with our RTV descriptor heap description, and we want to store that inside our com pointer here on this object here. RTV heap get address of, and error creating the RTV heap. The thing about these descriptors well, it doesn't actually say it here, but just trust me when I say that we need to figure out how much our pointers need to be incremented for this actual device, and we can use this function with specification of our type excuse me, and store that. So right now we have a heap that can be used to create views to our what do you call it? What do you call it? To our internal buffers. So a swap chain needs to be able to be resized. When it resizes, it needs to drop its buffers. Whenever we want to allocate buffers, we need the device, which means that we would preferably store a reference to our device. It will not go out of scope as long as the API has a reference count to the actual device underlying. So the life cycle is managed, and we can do a raw pointer which we store, and we shouldn't get in trouble here. And we simply store that pointer for future reference. So we then want to make a method that creates our buffers. We need to do a check here. If we do not have initialized our swap chain here, we would like to return and print a error message. Try to create buffers for uninitialized swap chain. Then we want to iterate over all our expected buffers. This will have a value once we have initialized. That's also another failsafe we need to initialize before we can even create the buffers. We will initialize whenever we create the buffers, we will make sure that we don't have a buffer already set. In that case, we want to release it. In order to swap chain, get buffer, access one of the swap chain's buffer. We will what do you call it? Does this return anything? Yeah, it returns an H result, so we can always evaluate if it doesn't work. We want to, as the swap chain here, to get a buffer with the index of I, and we want to store it in the RTV array here. And we, of course, want to for swap chain index I. And then we actually create the buffers. Let's see. We would, of course, like to be able to do that after we initialized. We would like it done automatically. Let's see if anything winds anywhere. Let's see, warning. Okay, we have something that we would like to release. Then for each buffer, that we have actually assigned after initialization, we want to call render target reset here. And we probably only want to do that if we actually have a initialized thing here. Let's see, that took care of the error during the live dump. Hello, it's no problem. I also created a GitHub repository that you can access. To the users on Twitch, I'm sorry, I'm not very responsive in the Twitch chat since this is primarily a YouTube exclusive. It's not part of my regular streaming series, which is of course both on YouTube and Twitch. Anyway, so we create our buffers here, but we created this descriptor heap here, and we haven't really mapped the descriptors in the heap. We would like to be able to assign a excuse me, render target view here, a so-called descriptor. We would need our resource, which will be a render target pointer, and then a render target view description. Which I think we could set to null. Let's see. Hello. Let's see. Default descriptor if possible. So we don't need to specify that. And then we need a CPU descriptor handle, meaning where do the CPU actually find this? So we will have to specify that. Descriptor handle, CPU handle, and we will ask our heap here, could you get us the start of your CPU address? And then, since we might do this for several buffers, we would like to change the underlying pointer a bit. The pointer here, we would like to increase. Let's see, is it? Yeah, it's a size t, so whatever we want to multiply with needs to be cast like that. We know that with the hardware-specific increments on the heap between the pointers is hard-coded into the API and is possible to retrieve during our initialization step. So we will simply, for each render target, iterate over these. Let's see, this doesn't return anything, so we should be good and do not need to evaluate that. So now we create our buffers on our swap chain, and we're so close to actually being able to interact with our screen and our window. We would like a function that allows us to drop the buffers as well. Let's see. And it will basically be what we did down here. So we will move this, move this, and simply call drop buffers. We also want to reset our render target heap, so that gets released whenever we're done. because now we create references into the heap. And we could do more functionality. A swap chain also needs a function called present, which is the actual call that flips the back buffer of the swap chain, as you can see here, into the screen buffer, and then in case of our double buffering method here, places the old screen buffer back as a render target. This is fairly easy to implement, since we will just get our thing here and call present. The sync interval is usually null, and we can do flags if we want to allow for variable frame rate and vsync screen tearing. We could do something called, let's see, dxgi present allow tearing. This flag here allows us to do tearing instead. Otherwise, you might get locked into your monitor refresh rate. And of course, whatever we call present, which sweeps the buffers, we would need to internally update our buffer index, since we will have shifted that. So yeah, whenever we call present, we swap to the next buffer, and we clamp that to the maximum buffer count. This is 2. So it will never be higher than 1. Okay. So now we can create our buffers. We can present our buffers. But what if we want to know where in memory to locate our current buffer? Usually we need that further down the line in terms of our pipeline. So we will do a method for that. We will do a method that returns the CPU-sided descriptor handle to our render target view. That is our current one. So that also takes into account our current buffer index. We will take our heap and ask for the start of the heap. We will again manipulate the pointer by increasing by the value of our current buffer, and of course the device-specific incrementation between the handles, and we will return that to the caller. Okay. Now we're really close at really doing something. And by something, I mean doing a bit of drawing to the screen, or I guess you could call it drawing, but interacting with the window. As you might recall, the window is just white right now. We have set up our swap chain, and we want to, for instance, show that we can actually present something. Maybe our render API needs something like a update draw call. which we will implement here, that will run during our application runtime here. Let's see, we don't need the Windows procedure. We need the update function here, render update draw. And we could combine our stuff here. Yeah, I'll do it in this episode. So far it's a bit long, but we will prioritize getting something to the screen. Yeah, it's been an hour. It's a bit long, but the swap chain is a complicated object. So yeah, I'll just do that and then I'll upload that video. So in order to write to our swap chain, we need to do some resource handling in DirectX 12. That's a separate topic on its own, and we will be sure to revisit it. But in general, you need to do so-called resource barriers, which make certain that since we have the possibility of defining resources as all kinds of types with just the correct view/descriptor, then we would like to make sure that the objects are in the correct state when we want to use them for something specific. So I'm unsure whether this will give us a error, but we will try it out because the resources might not have the correct state. Oh yeah. Okay. I think actually that this will be a separate video because we also need to do changes to our command queue and slash no, not slash, rather our command list, and to keep episodes short, uh, um, we will segment off here. I'm sorry for the confusion. Be sure to watch the next episode because we will start doing a bit of output to our screen. I'll try to keep that episode short. I'll, as always, mention that if you found this helpful, inspirational, or entertaining, or anything else, feel free to comment, like, or subscribe, or support the channel. And I'm just gonna upload the video to YouTube. Since we here on the stream will continue once I get set up in terms of the upload. And let's see, it's part 7. Creating the swap chain. We did indeed create it. There we go, that's in the queue. All right, I'll just check in on Twitch while we update the let's see. Okay. So part 7, creating the swap chain. Let's commit that and push it. And our video got done on the YouTube platform as well. Let's see. I'm just gonna do some stuff here in terms of the playlists. Okay, I think we got set up. Okay, it's currently processing in terms of the HD resolution. Okay. Since there are no comments, questions, or anything in the chat, I will continue on the next part. Hi, and welcome to the next part of this video series. During our last episode, we created the swap chain and its buffers. We created a render target view descriptor heap where the GPU pipeline and also the CPU can find the references to our buffers on the swap chain. I wanted to do some basic output stuff. I'm sorry. During the last episode, but it spanned an hour, and yeah, I decided to end the video right there since since it had taken a long time. We would like to test our things out whenever we present or get our pipeline ready to present our current back buffer after we have done rendering to it. We before that we will simply clear it. We will try out using a clear color of black. But suddenly, as I decided that I wanted to do that, I realized that our command list here needs a way of kind of like returning not a command list but a graphics command list, since that's what we record our that's the interface that we record our commands from. So we will do a few changes. We will do an inline function here where we return the interface of a graphics command list pointer. And we will simply call it command gfx command, and this will return our pointer here. But cast as a graphics command list. since we are allowed to cast our command list to the graphics command list, we can simply do that whenever we want to do a graphics call. We will use the call as you saw in the wrapper. We will do command list gfx command, and we will do a clear render target view, and we need to excuse me, supply a D12 descriptor handle on the CPU side. CPU descriptor handle. As you saw during our last episode, the swap chain will actually be able to supply what is our current render target and what the handle is to that. So let's get the handle from our swap chain. By getting our method here. And our render target will take that handle. It will take our color, which we just set, the clear color. And then it would like some information about the number of rects that are specified in a pointer afterwards. We don't have any such kind of stuff. So therefore, we won't do that. The problem is that we might end up in a situation where this may get called before we can initialize anything. Let's see. We might have an error here. Yeah, we did. Let's see, does it relate to... Well, okay. As you can see over here, I talked about that in a previous episode, our memory usage just keeps increasing, which means we have a memory leak. That is because we keep on recording this command to our command list. That's not great. We also need to couple our command Q and our command list. And our command Q here has a method where we can call execute command lists. We can specify the number of command lists. We can specify one, and we can specify our command list. And let's see. It wants it to be const. So let's just cast it. Let's see. Doesn't this work? Well, okay. Let's see. Usually we need to do this instead, perhaps. Yeah, there we go. This will probably crash. Now, as you can see here, it will also crash, but because we haven't handled our stuff correctly. Anyway, as you can see here, we must close the command lists before we execute them. This was a demonstration of our D12 debug layer. So we will ask our command list to get the pointer here. Okay, it probably also needs to be called on the GFX command list. Oops. Close. Let's see. The stuff can't be, let's see, can't be called on a closed command list. So now we need to open it. Yeah, okay. We would actually want some method on the command list here in terms of resetting the allocator. Reset command list. Where we simply reset the allocator and call a reset here. Mind you, this is not a release, it's a reset. And we call the GFX command here to reset also this. Again, it's not the com pointer function. Let's get the allocator, supply that, and a null pointer for the target pipeline, standard pipeline state. And we of course need to call that function afterwards. Reset command list. There we go. Now nothing happens, but let's see what our error message is. As you can see, the system whines that we're trying to reset the command list allocator before it's done using it. So this basically means that our between these two steps here, on the CPU side, everything is happening too fast. So we need some kind of wait method to handle that. And we can simply do something like while our command queue get fence get completed value is lower than our command queue current fence local value, we call the pause intrinsics. Let's see, we still have the same problem. Using rendered, yeah, so the problem is that we haven't transitioned the resource state, as I mentioned. I think it was during the last part of the episode before. So you might remember that I said this might give us an error, and that's because we need to handle the resource state. The resource state is common, and we want to set it to the appropriate resource state. For that, we need a resource barrier. A barrier, as you might recall, controls a resource state. Let's do a resource transition here. Let's do a zero flag thing. And we need some information about our resource. Which resource do we want to change? Let's do a null pointer for now. The sub-resource can usually the sub-resource is an integer, I think. Right. Yeah. We will not care about that. We will also set the state before. Actual state, comment / percent. So this will be our percent state. D3D12 resource state percent. And we want to transition it to the state after, where it's the render target. The problem is that we not only want our handle here, we also want the actual resource. So we would like a way to get a resource pointer as well. Let's do this inline where we simply get current render target, where we return the render target's current buffer, current buffer address. There we go. Not application or render API. Yeah. So let's set that to our swap chain here. Get current render target. Afterwards, we would like to be able to actually in part do the present stuff, and then kind of like when we clear the render target, we of course need to actually do this. Let's see, we will ask our command list here to do a gfx command where we transition. Isn't that it? Let me see. As far as I remember. Okay, it's the resource barrier call. We will do one, and we will change this barrier here. That will be done before we write anything. Then we want to ask our swap chain to present whatever we did with our render targets. Let's see. No, that will be done after we have done closing the command and executing. Then when we are sure that everything is done, we can actually reset the command list. When we do this, we would like to transition the resource back into a present state. So we set it to a render target state. We try to clear the color of it. Then we set it back to the present state. Then we close the command list. Let's see. Then we close the command list, execute the commands, try to call present, and we wait for the allocator to be done, slash not be in use, and we try to reset it. Let's try to see if that compiles. And you can see now we have a black screen. We still have some errors in the background, but at least we actually managed to do something with our application. Everything still crashes, and that is because we have some commands in okay, let's see. When do we start running into problems here? Let's see. And the problem is probably that we don't increase the fence value, therefore we have no weighting. I'm pretty sure that's the problem. Yeah. So we would actually like a wrapper for this call here. Let's see. We would like something like a internal execute command list, and let's just take a pointer to the command list that we actually want to execute. We will execute the command list in our bundle here, and as you remember, it wants a constant pointer that doesn't change. This is kind of hacky. Let's see. And it actually expects the address of the address. Also, we want to increase our current fence value since we know that we are executing a command. So we know which fence value to wait for. We will also tell the pipeline that whenever this series of calls gets done, set this fence to our current fence value. So on the GPU, whenever it's done doing this execution here, it will increase the underlying fence to this value. This means that the CPU can always wait for our actual fence value to reach the current fence value stored internally on our command list wrapper. So right before we weren't actually doing any waiting. Let's see, m execute command list, m command list, get the pointer to that, and we might now have sufficient synchronization. As you can see, we have no errors anymore. During our application runtime, we have a black screen, which means that our clear color is doing great. We still have a crash because, as you can see here, we reference an object that is in flight on a command queue, i.e. our render target. So this means that whenever we close our application, we actually want to quote unquote flush the command queue, and of course make sure that we are not rendering anything in particular. Okay. But we will fix that later. I was about to show you that this actually is because we are doing something to our render targets. And as you can see, I managed to clear the color red. We can even do something that epilepsy warning here. Don't watch this if you have any of such problems. We will do a current index, which will be 0. Let's do test variables here. Temp test vars. During each update draw, we will set this to its own value divided by 2, or rather wrapped around 2, and we will do a call here. If it's 1, we do this, otherwise we do black. As you can see, we had some flickering in the start. I actually think we still have flickering, and if I resize it, move it, you can actually see the swap chain pausing for a bit, and actually swapping between the black and red color. Yeah. So this actually works. Let's just clean up the code here. The last thing that we want to do is to make sure that whenever we do like this, whenever we call release on the application, we make sure that nothing is in flight. Let's see. Oh yeah, okay. The flushing is actually let's see. So during our swap chain here, whenever we call release, we drop the buffers, drop the stuff before we call release on the swap chain. We make sure that everything is done. Let me see. Maybe we want to do some extra flushing. We might have, yeah, okay, we can do a function here that is called flush hue. That is basically where we kind of tell the command queue to flush. Let's see. We can ask the system to perform a fence. Let's see, signal to the fence, where we will ask it for our current value here, +1. And we will do this for as many times as our G max swap chain buffers. Okay. Flush the queue. And I think we should be good now. In terms of not getting any crashes, okay. Well, maybe it's because we simply exit the application. No, that doesn't. Let's see. Yeah, it pertains to the way that maybe we want to wait for the fence anyway. Let's see. Maybe it's the order that we do the releasing in. Okay. Nope. Maybe it's because we don't want to close the application the way we do. Because why would it why would it even call that part of the update step? I mean, it's a minor bug, but I want to fix it. So when oh, maybe it's because they go out of scope too early? Maybe we want, well, we did that before. Um, it's like it's crashing there every time. Does it do a, well, it should only do this draw call. If ever we're running. Let's see if we do a check. Nope. There's some bug here in terms of the way that our calls get ordered. I won't end this episode on a bug. I think this is fine. We aren't running in our application. We will call on destroy. How can we actually, let's see. So if we set a breakpoint here, we do not have a problem yet. Let's step into this. How do we end up here? Well, it's obviously related to the running clause. We shouldn't be running update after we posted the let's do if we are running, we can do the update draw step. Okay, let's see. How come? Oh, wait a minute, wait a minute, wait a minute. I know why. If we actually have a command queue, because this gets called again, that is why. No need to try to do it twice. We could also do a check inside of this if it's even valid. Then we do this, otherwise it's not valid. Let's just do like that. Whoops. So it was because the post quit message got translated, and then we ended up in a update draw call again, even though our application wasn't running. Yeah. Let's see, do we have any live objects? No, we don't. Okay. So during this episode, we made changes to our command list structures. We added the method to reset the command list allocator, and then resetting the command list itself via the graphics command list call, where you need to specify which allocator to use when the command list is reset. We also did some functions on our command queue, where when we want to execute a command list with our internal wrapper function, we take the command list that we want to submit, we submit it to the queue, and we expect to wait for a fence for this specific frame. Since we at frame 1 will generate frame 1, we increase the fence value to a 1, and we will tell the fence, or rather tell the command queue that whenever it's done with the work on this command list, it should signal the fence that we have achieved this fence value and update the fence value. We added a flush queue function in terms of closing down the application in case we need to do that, where we make sure that for every potential buffer in flight, we simply do pseudo work on the command queue. We tell it to wait for this. Let me see, maybe I actually should let's see, maybe I should have done a multiplicative. Yeah, it's not +1, it's +I. Anyway, we tell the command queue to signal the fence whenever it gets to these values. Since there are no commands, it will reach the fence fairly quickly and simply flush the command queue. Nothing will be inside the command queue. Yeah, so we changed that. Added some functionality. So now we have also a update step where we take our current render target from our swap chain. We transition its state so that it's not a present target anymore. The first time it's used, it's in the present slash common state, but that doesn't matter. And we set it to a render target state. We tell the command list that we want to make this transition. Then we get the pointer to our current render target, and we store a command that tells the that records to the command list that we want to clear the render target with the specific handle to the specified clear color. We have a test variable here that we don't need. We then do another barrier transition on still the same render target. Now we don't want to render to it anymore. We want to present it to our screen. Therefore, we record this resource transition. And since we feel like now we're done in terms of recording commands, we close our command list and we send it off to execution, which was the function that I just showed you. Then we want to present our current render target to our screen. Then if our CPU is too far ahead of our GPU, we will wait for it. And then when we are certain that there is nothing in use in terms of the command list recordings and the specific command list allocator, we of course reset that. We can only be certain whenever we're sure that the CPU is not too far ahead, since we only use one command list. If you had several command lists, you could of course do more work. When we close our application, we check if we need to flush, we release our swap chain, our command lists, and so forth. We also changed this part of the application. We only want to do the renderer update draw whenever we are running, since it will give us a lot of different null pointers if we don't do that. Since we on the message destroy start the releasing process of the renderer resources, it would only be wise to check if we already set this flag to false and therefore shouldn't do another update draw call. Yeah, that's it for this video, minus debugging and everything else. It took about 45 minutes and we now have output to our screen. We also have a simple pipeline in terms of doing graphics commands and record them. So we're basically ready to dive into more in-depth topics in terms of DirectX 12. These are the fundamentals in terms of resource transitions and recording of commands. Yeah, but we will of course need to couple pipelines and shaders and a lot of fun stuff, so that we can actually do something else than just clear the render target with a specified color. So yeah, we will do that in future episodes. I think that this will be it for today. If you found any of this helpful, inspirational, entertaining, or something else, please leave a like, comment, or even a subscription. Feel free to check out my other live streams and make requests in terms of this content. Hopefully I'll be seeing you around. Thanks for tuning in and take care. Yeah, and oh, by the way, the repo will be updated, of course. All right, take care. Bye-bye. As for the stream, I will do a bit of winding down, but I think that I am done for today. I've spent most of the day providing a initial setup for our DirectX 12 application. I'll just hang out here while I upload the video and do the commits and so forth. Let's see, what did we reach? Did we reach part? Let me see on the repo here. Part 8. see. All right. Oops. Excuse me. All right. Let's just do the repo stuff here. R8 rendering to the screen, presenting the render target buffer to screen. Let's commit. Oh, okay. Actually, it's easier just to push that button. All right. To anyone watching the stream in the future, thanks for tuning in. If you found any of this helpful, feel free to comment, like, or subscribe. Hopefully I'll be seeing you around. No matter what, stay strong, stay focused, have fun.